It's a harder course, so we can emphasize this a lot. It's much harder than dynamics. This is the least that I should say. So I'm trying to give some motivating applications. Maybe I should change this lecture later on because sometimes it seems to be attractive, but the course is not that attractive. So anyway, don't get misled by this lecture or these applications. But anyway, we'll keep talking about it. Yeah. I mean, it's not clear at this moment. This lecture will cover two main topics. What is geometric control and why geometric control for engineers? How an engineer can benefit from this very mathematical control theory. This is just an introduction. We'll not go through deep things, but hopefully we'll give you an idea about. Yeah. So if we want to put it in precise terms, this lecture will give you an idea about what can you achieve after you finish this course. So the course per se may not be about these topics in particular, but after you finish the course with all of its mathematical challenges and hardships, you will be able to achieve these things. But at first, we'd like to give a little bit about what is geometric control. So it's a mathematical control theory. It's almost pure math, and just we're writing our control theory in a mathematical language, very abstract. It's concerned with dynamical systems evolving on nonlinear curved spaces, and by this, what I mean is when you have your state space, your states x1 up to xn, they live in some space. When you compose these states x1, x2, x3, x4. Typically, this is like a flat space, like x, y, z, this room, for example. Some systems, they don't evolve on a flat space, x, y, z, they evolve on curvy spaces. And by curvy space, what do you mean by curvy spaces? If you have any system that has rotational degrees of freedom, which almost all systems in mechanics have rotational degrees of freedom, they will evolve on curvy spaces. What do you mean by that? Let's consider the simplest ever system. This is the pendulum, right? So this is your differential equation, theta double dot g over L sine theta. And in even some rigorous books, you will find them saying where theta belongs to R, right? Theta is just a number. Theta is a number, right? But a number, we think that it belongs to R, the real line. Actually, it's not. Why? Because here's the real line. Here is the point 0, here is the point 2 pi. They are not the same point on the real line, obviously, right? This is 6 point something or whatever, and this is 0. Whereas on the circle, which is a curvy space, obviously, 0 is equivalent to 2 pi, right? They are the same point. So intrinsically, the pendulum dynamics evolves on the circle, which is obvious, right? And the circle is a curvy space, it's not a flat space. Mathematicians call the circle as S1. Maybe some of you have taken dynamics and they are familiar with this notation S1. Okay, so we're saying now a very big statement, which is all systems having rotational degrees of freedom, they don't evolve on flat spaces, they evolve on curvy spaces. And we're saying that mechanics, this is covers almost all systems in mechanics. It's very hard to have a system without rotational degrees of freedom. So now we need a tool to study the calculus on a curvy space. By calculus, as you guys know, differentiation and integration. Interestingly, if you have a function or a vector value function defined on the circle and you want to differentiate it, just differentiate the function. That's nothing fancy. It's very different from differentiating the function on the real line. If you apply your usual definition, you will get a wrong answer, basically, okay? So we need a mathematical tool. So we're stuck with this guy. I want to study the system while evolving on this curvy space. I need a mathematical tool that allows me to do calculus on that curvy space first, without doing sophisticated analysis or control or whatever. This is the differential geometry. So if you need a mathematical tool to perform calculus on curvy spaces, this is differential geometry, which is a hard topic in mathematics to mathematicians themselves. So this is a hand-wavy definition of geometric control. If somebody in the street asks you what is geometric control, this is the answer to people in the street. It's just differential geometry plus our control theory. So it's our control theory, the notions of stability, controllability, observability, and everything. And by the way, you don't need to write down these things. I will post, we're recording, hopefully we'll post the videos, but at least I will post the slides. But the things that are not in the slides, you're welcome to write, of course. So anyway, it's our control theory, which is the notions that you are familiar with. Stability, controllability, observability, all these kinds of notions, feedback, written in a mathematical language, written in the differential geometry language. Okay? Why? Because, like I said, almost all systems in mechanics, they evolve on curvy spaces, and we need this language to better describe the system. This is the book from which we, so a big chunk of the course will be from this book. I will not be following one particular book. I'll give you the references at the end, but a big chunk of the course will be from that book. It's representative for any topic, for any book in geometric control or geometric mechanics. It's a yellow Springer book where, yellow Springer means it's very mathy subject. And we have a quote here in the preface of that book by Leonardo da Vinci, which says, "Mechanics is the paradise of mathematical sciences because by means of it, one comes to the fruits of mathematics." There are many things that can be extracted out of this statement. First, it's two-way interaction. In mechanics, we really benefit from mathematical tools because we start. We want to do analysis, like on curvy spaces here for in this example, and we don't have a mathematical tool, so we're going to wait for mathematicians until they come up with sufficient mathematical tools for us. So this is how mechanics benefit from mathematics. Actually, mechanics from day one is a mathematical subject. But it's actually the other way around also, in the sense that also mathematics benefit from mechanics. Like you see here from this statement, it says that mechanics actually provides a paradise of rich applications to mathematicians. In fact, if it wasn't for Einstein's general relativity, all Riemannian geometry would have gone to oblivion. I mean, nobody will ever hear about Riemannian geometry if we didn't have Einstein's general relativity or how to apply this, Riemannian geometry in mechanics. So we provide very rich applications to mathematicians, and we benefit from these mathematical tools. To me here, it's beyond this. To me, as an engineer, it says the following: if I have enough patience to study this very hard subject, I will have some fruits at the end. Actually, today I'll give you a little bit of a touch on these fruits. So let's answer this question first, or give a glimpse on this question. What is geometric control? We had our hand-wavy definition, just differential geometry plus control theory. Okay, so let's have some basic elements or some basic definitions of differential geometry. The basic element, actually, in differential geometry, which we're gonna talk about a lot, or it will be just like our bread and butter in our course, is the manifold, the word manifold. Okay, what is a hand-wavy definition for a manifold? We have seen this in our dynamics course. It's a space that is everywhere locally diffeomorphic to Rn. Okay, and here we need to be, to understand very well the meaning of every word. So let's see. It's a space, so it's like this table. This is a space. This room is a space. Okay, that is everywhere. It means that at every point in the space. Okay, what happens at every point in the space? Locally around that point. What happens locally around that point? So locally around the point, it's diffeomorphic to Rn. What's Rn? Rn is the Euclidean space. It's like XYZ, the flat space. So we're saying it's a space that is everywhere at every point. Locally around the point, it's diffeomorphic to a flat space. What do you mean by diffeomorphic? Here is the definition of a diffeomorphism. It's a smooth relation. You can differentiate it many times as you want. It's one-to-one, so here is your manifold, or a neighborhood around the point, locally around the point. Here is the flat space. It's one-to-one in the sense every point in the manifold in this neighborhood maps to only one point. Okay? So this guy maps to this guy maps to this guy, and so on. So, and we have an inverse. So this point maps to this point, and this point maps back to the same point. And going forward smooth, going backward smooth. So it's as if the two sets are almost identical. because every point here corresponds to only one point there. And I can go forward, I can go backward, very smooth, so they are pretty much equivalent. In fact, mathematicians, when they want to say that these two sets are equivalent, they look like each other, they try to prove that they are diffeomorphic to one another. When they say these two sets are diffeomorphic to one another, they really mean that they are equivalent. Okay, so what do we mean here? So we're saying that everywhere, at every point, locally around the point, your manifold, your space looks like a flat space. So it's very close to the Earth. Like if you zoom out, it's really curved. But when you zoom in, like this room is on the Earth, right? And if you look around, this is really flat, right? So it's something like that. Which means the following. Wait a minute. You're saying that your space, the curved space, locally looks like a flat space. So why are you making a big deal and want to have an entire thing about curved space? Because the straightforward approach is that you just said that by definition your space is locally looks like a flat space. So why not using these flat coordinates, which are typically in mechanics positions and velocities, as your coordinates? And now you're evolving locally, yes, you're evolving on what? On a flat space, right? Use your classical control theory that you are familiar with, which was developed for systems evolving on a flat space, and you're done, right? Yeah, this is actually what we do most of the time. This is the classical control theory that we do, but it's essentially a local approach, okay? If you're happy with this local approach, that's fine. But you will miss the global picture, because you're just zooming and seeing this neighborhood around the point. You're not seeing any global picture. So if you want to get the global picture, then you need to go to differential geometry and geometric control. So I will move to the second point, which is why geometric control and how you can benefit from it. And the first benefit is what I just said. It will give you a global intrinsic assessment of the system behavior. If you want to have a global picture, there is no way to do a global picture for a system evolving in a curved space without geometric control. There is no way. Okay? And we're going to see a very concrete example, very simplistic example that will, it shocked me when I saw it the first time. But even if we do local analysis, and this is my favorite part, sometimes when we apply geometric control theory, we get very interesting stuff like the nonlinear controllability and motion generation in unactuated directions. You have some directions over which you don't have an actuator to push you in that direction, even though the geometric control will tell you how to move in that new direction. Combined with averaging theory, geometric control and averaging together, they will give you very useful tools to analyze time-varying systems and what we call vibrational stabilization, vibrational control. I'll give you an example of each one today, hopefully if we have some time. So let's go to the first one, about the global thing, okay? And this is an attitude control example. It's the simplest control system ever. You have just 1 degree of freedom. Maybe it's the angle of a satellite spacecraft, or it's the angle of a robot, or whatever. Just one angle, 1 degree of freedom. Theta dot is your omega angular velocity, and you're actuating your angular acceleration, the torque. U is the torque, right? You have unit inertia here, okay? This is the simplest realistic control example ever. And it's linear, okay? It's linear. And if we want to be precise, now after we have just 5 minutes introduction, we want to say this system, what are the states of this system? It's theta and omega. So theta and omega lives where? Theta lives in S1, in the circle, and omega's angular velocity is just a real number, okay? So theta and omega lives in S1 cross R. Okay, very good. So this is the real intrinsic, S1 cross R is like a cylinder, right? Because it's a circle, and at each point in the circle, you have a real line. So this is a cylinder, an infinite cylinder. Okay, this is your state space. Okay. It's a curved space. This is a linear system, very simplistic. And we need to achieve this task, which really I can give it to an undergrad, even not senior undergrad, even like in the second year, right? Please, for this system, I will not give this statement. This system, please achieve global asymptotic stability. Make the system globally stable. What do you mean by globally stable? We mean if we start with any point, any theta and omega, we go back to the desired theta and 0 omega. Okay? Achieve global asymptotic stability. This is super easy. Why? Because I will do state feedback, whatever you want to name it. State feedback, K1 times theta, K2 times omega, or PD control, right? PD. Whatever you want to name it. Okay, this is the standard thing in our undergrad. State feedback, PD, just plug U here, back, to get this closed loop dynamics, second order system. Happy because this is, we kill this to death in our undergrad, second order system, mass spring, right? So if I just have a positive spring and positive damping, I'm done. The system is globally, asymptotically, exponentially stable, right? And this hierarchy is important. So from any point in the theta omega space, I start from any point, I go exponentially fast to my desired location, which is the origin here, theta equals 0, okay? This is a super simple example. Except that actually it's wrong. This is not the case. I mean, we did it in our undergrad, but in our undergrad we weren't that precise. This is wrong. It's not the case. Actually, this paper, using geometric control theory, tells you the following fact. This is just taken from the paper. What's that? There cannot exist a continuous vector field in a compact manifold that has a globally asymptotically stable equilibrium point. In our course, we will learn how to read this language. This is the point. Let's try to interpret this. There cannot exist what? A continuous vector field. To us now, vector field means a differential equation. Okay? So a differential equation, your system here. The differential equation representing the system. Continuous, so these are continuous. So U is continuous in theta and omega. It's a simple relation, linear relation. It's continuous, of course. It's not discontinuous. Okay, if you have a continuous system, which is most of our systems are continuous, on a compact manifold, this is a little bit weird now, we didn't have it before. For us here, any system that has a rotational degree of freedom will always evolve on a compact manifold. So to me here as an engineer, compact manifold means the system has rotational degrees of freedom. This guy does, and almost all systems do. Okay, if you have a system that has rotational degrees of freedom, it's continuous, which almost all of our systems, it can never have a globally stable equilibrium point. It can never have. This is a very strong result. It means that almost all your systems, you can never aspire to achieve global asymptotic stability. You can never achieve global stability. This is very strong statement. The interesting point about this paper, of course the result is very important and very impactful, but the interesting point is that it wasn't actually hard to get it. These folks, the authors, they just put in front of you the definition, just the basic definition of each one of these words. What's the definition?